Right then. So we've spent a few sessions in calculus by this time, learned the basic tenets of limits, continuity, differentiability, and now so that was related to one kind of a character of a function. Now we would examine the trend of a function. Now in context of trends, I'll define a few things for you. Suppose there is a function y equal to fx. Suppose there is a function y equal to fx, and let's say we are talking about, by default, we are talking about, points that are in the domain of description of the function. Now, in the domain of the function, if I select 2 points x1 and x2, any 2 points x1 and x2 are selected in the domain of the function, such that for every x1 less than x2, if f of x1 is less than or equal to f of x2, that means as x increases, fx does not decrease. If f of x1 less than or equal to f of x2, then we claim that fx is monotonically increasing in this interval. Say x1 and x2 could be 2 points selected in a to b, in an interval a to b. So if x1 and x2 are any 2 points in the interval a to b, and if for every x1 less than x2 I find f of x1 less than or equal to f of x2, then fx is said to be monotonically increasing in the interval a to b. Monotonically increasing, sometimes we simply say non-decreasing. We sometimes also refer to this as increasing. They all mean the same. So that's what is meant by a function being monotonically increasing in an interval. Similarly, if for every x1 and x2 selected in the interval a to b, which is, let's say, part of the domain of the function, if I find that f of x1 is greater than or equal to f of x2, if f of x1 is greater than or equal to f of x2, I say fx is monotonically decreasing in the interval a to b. We also call monotonically decreasing as non-increasing. We also write this sometimes as simply decreasing, right? So this is what is meant by a function being monotonically decreasing in an interval, which means, say, y equal to fx versus x. Say this is a function which goes as follows. In the interval a to b, if I select any x1 and x2 such that x1 less than x2, I find that f of x1 does not exceed f of x2. f of x1 does not exceed f of x2. f of x1 does not exceed f of x2 for every x1 less than x2 in the proposed interval. And when this happens, the function is said to be monotonically increasing. In fact, equality of the function at two or more points is an acceptable fact for monotonicity. Y equal to fx, suppose, versus x. If I have a function like this in the interval a to b, something like this, where between c and d the function maintains a constant value. Between c and d the function maintains a constant value. This also is monotonically increasing. This also is monotonically increasing in the interval a to b, even though the value of the function at two or more points may be the same. But for sure, as x increases, fx does not decrease. Non-decreasing function, that's monotonically increasing, right? Similarly, if I had something like this, y equal to fx versus x in the interval a to b, and if say x1 less than x2 for any pair x1 and x2 selected in the interval a to b, if for every x1 less than x2 in this interval, if I find that f of x1 is greater than or equal to f of x2, then we say that the function is monotonically decreasing in this interval. Monotonically decreasing in the interval a to b. Monotonically decreasing is also the same as non-increasing. It's the same as non-increasing. That means as x increases, the value of the function at least does not increase. As x increases from a to b, the value of the function at least does not increase. That's the important thing. Say, if I had something like this, in the interval a to b. In the interval a to b, do you realize that even though the function maintains a constant value at a certain set of points, the function is a monotonically decreasing function. It's non-increasing. It is at least not increasing. So this is also monotonically decreasing. This is also a monotonically decreasing function. Say, now I look at fx equal to box x. Fx equal to box x. See, the graph of this function is in the interval 0 to 1, it is 0. From 1 to 2, it becomes 1. From 2 to 3, it remains 2. And so on and so forth. This is the graph of y equal to box x. This is monotonically increasing. This is monotonically increasing. Increasing. That means non-decreasing. That means non-decreasing or simply increasing. So box x is monotonically increasing. Now, we have another definition, another fact, jargon that we want to associate with this kind of trends, which is a strictly increasing function or a strictly decreasing function. What is meant by a strictly increasing function? So again, all refer to the domain of definition of a function. If for every x1 less than x2, say in the interval a to b, for every x1 less than x2 in the interval a to b, if one finds that f of x1 is less than f of x2, f of x1 is less than f of x2, then the function is strictly increasing. Right? That means something like this. A to B. Say if I have this x1 and this x2, very clearly f of x1 will always be less than f of x2. This condition would be met for every x1 less than x2, f of x1 would strictly be less than f of x2, then the function is said to be strictly increasing in the interval a to b. Similarly, if I had something like this, a to b, then for every x1 less than x2, for every x1 less than x2, you find that f of x1 is greater than f of x2. If f of x1 is greater than f of x2, then the function is said to be strictly decreasing, strictly decreasing. In the interval a to b. This is what is meant by strictly increasing and strictly decreasing in a certain interval. Now, this description which I laid down for you earlier, is it strictly increasing? No. This function is not strictly increasing, but it is monotonically increasing. This is monotonically increasing, but not strictly increasing. But not strictly increasing. Similarly, y equal to box x is monotonically increasing but not strictly increasing. See, one thing for sure, if a function is strictly increasing, it is monotonically increasing. But if it is monotonically increasing, it may or may not be strictly increasing. That's the important thing to understand, right? Now, once you understand this terminology, let's look at the model that will help us relate to this terminology. If one finds suppose this is a function, something like this. A function like this, right? And if you find that the tangent at every point makes an acute angle with the positive direction of the x-axis. This is a tangent made at a given p, say at a given x. At a given x, floating between a and b, the slope of this tangent is given by f dashed x. And if for every x in the interval a to b, if you find that f dashed x is positive, If for every x in the interval a to b, if you find that f dash x is positive, then you can conclude that fx must be strictly increasing. If the slope of the tangent at every point is positive, if the derivative at every point of this interval, assuming that the function is continuous and differentiable in the interval a to b, if you find that f dash x is positive at every point, then you can claim that fx must be a strictly increasing function in the interval a to b. Similarly, if a function is differentiable in an interval a to b, this is the tangent drawn at a certain x. At a certain x, this is the tangent drawn. See. And you find that the slope of this tangent is negative. For any given x, f dash x is less than 0. Isn't it? Slope of this tangent is negative. This tangent makes an obtuse angle with the positive direction of the x-axis, and if you find that f dash x is less than 0 for all x in the interval a to b, then you can conclude that the function must be strictly decreasing in this interval. Decreasing in the interval a to b. Right? In fact, let me also mention another fact. Can I wipe this off? Right? So one understands the calculus implication of strictly increasing, strictly decreasing for a function which is having a positive derivative at every point in an interval. The function has to be strictly increasing. If it has a negative derivative at every point in an interval, the function has to be strictly decreasing in that interval. In fact, let me also mention that if I have a function y equal to fx, and if one finds that in an interval a to b, say this is an interval a to b, if one finds a set of discrete points c. See, in this case, f dash x is positive everywhere. Let's say, save a point c for example, right? If f dash x positive for all x belonging to a to b, except for a set of discrete points c. C, where f dash x becomes 0. Say for example, this is a discrete point c where f dash x is becoming 0. At all other points f dash x is greater than 0. Then at one or more isolated points, these c's must be isolated points. They must not constitute an interval. As long as they do not constitute an interval, and if one finds that at these points f dash x is becoming 0, then the fact of strictly increasing is not affected. The function will still be strictly increasing, even though you might find a few points c in the interval a to b that do not constitute a continuous interval. These c's should not constitute a continuous interval. As long as they don't constitute a continuous interval, as long as these c's are discrete, these c's should be discretely placed in the interval a to b, and even though f dash x becomes 0 at these discrete points c in the interval a to b, fx will still be looked upon as an increasing function, strictly increasing function. Yes or no? Right? So something like this. This is strictly increasing even though you find f dash x positive at all points, save a point C where f dash x becomes 0, the function is still strictly increasing in the interval a to b. If, however, I have something like this, in the interval a to b, I find a set of continuous points from x equal to e to x equal to f. I find a continuous set of points where f dash x becomes 0. Then the function will not be looked upon as strictly increasing in the interval a to b. This is monotonically increasing but not strictly increasing, because these c's are not discrete anymore. These c's are a set of continuous points in the interval a to b. The entire interval e to f, constitutes these c's where f dash x becomes 0. So if these c's constitute a continuous in the interval, a continuous subinterval in the interval a to b, then the function will not be strictly increasing, it will be monotonically increasing. But if these c's are only discrete values, they do not constitute an interval, and you find that at these c's f dash x becomes 0, then you can still claim that the function is monotonically increasing. And whatever I have said for monotonically increasing is also true for monotonically decreasing. So why don't you just make a note of a few things here. One, please note down, a function which is differentiable in an interval a to b is such that f dashed x is greater than or equal to 0, or rather f dashed x is greater than 0, such that f dashed x is greater than 0 for all x belonging to a to b, except for a set of discrete values of x for which f dashed x becomes 0, fx is said to be strictly increasing. In the interval a to b, fx is then said to be strictly increasing in the interval a to b. That means f dashed x essentially should be greater than or equal to 0 in the interval a to b for all x except for some values of x where f dashed x becomes equal to 0, and these values of x for which f dashed x becomes 0 should not constitute a continuous interval. They should be discrete values of x for which f dashed x becomes equal to 0. At all other values of x, if f dashed x is greater than 0, then the function is looked upon as strictly increasing. Similarly, if f dashed x is less than 0 for all x, except for some x where f dashed x becomes 0, some discrete values of x where f dashed x could become 0, then also the function is strictly decreasing. That means f dashed x less than or equal to 0, where it's less than 0 for all x except some discrete values of x where f dashed x could become equal to 0, then the function is said to be strictly decreasing in the interval a to b. Right? So, let me give you an example. fx, for example, x minus sine x. F dashed x is 1 minus cos x. F dashed x is 1 minus cos x. Very clearly, this is greater than or equal to 0 for all x, except it will be greater than 0 for all x except say x equal to 0 plus minus 2 pi plus minus 4 pi, f dash x becomes equal to 0. These are discrete values of x. They don't constitute a continuous interval. These are discrete values of x. If at these discrete values of x you find f dash x becoming equal to 0, then you can still claim that the function is strictly increasing. So x minus sine x, f dash x could become 0 for some values of x, but those values of x are discrete. For other values of x other than these, f dash x is strictly greater than 0. F dash x is strictly greater than 0, and which really means that fx must be a strictly increasing function. Function of x. Yes or no, right? Say if I have fx equal to x cubed minus 3x plus 8. I want to find the intervals in which fx is strictly increasing, intervals in which fx is strictly decreasing. I would have to look at the sign of f dash x. Look at f dash x. F dash x is 3 into x squared minus 1 which is 3 into x plus 1 into x minus 1. Now as far as the sign scheme of f dash x is concerned, you can obtain that from what's referred to as the wavy curve method. The nodes are minus 1 and plus 1. This is the wavy curve for f dash x. The scheme of signs for f dash x. F dash x is negative in this interval, positive in this interval, positive in this interval. Very clearly, f dash x is greater than or equal to 0 when x belongs to the interval minus infinity to minus 1. Union 1 to infinity. Then f dash x is greater than or equal to 0, and it's becoming 0 only at discrete points at 1 and minus 1. Therefore, that will not affect the strictly increasing character of fx. So f dash x greater than or equal to 0 in this interval. So in these two intervals, to the right of 1 and to the left of minus 1, fx is strictly increasing. And in the interval minus 1 to 1, in the interval minus 1 to 1, you can see that f dash x is less than or equal to 0. Fx then is said to be strictly decreasing in this interval. Fx is then said to be strictly decreasing in this interval. How about it, right? Now, so this is as far as a function being strictly increasing or decreasing in an interval is concerned. Let me also define what is meant by a function increasing at a point, increasing at a point. Or decreasing at a point. This is a point x equal to a, and I want to see if a function is increasing at this point or decreasing at this point. Then all that one needs to do is, if one can find an open interval surrounding a, say h units to the left of a and h units to the right of a. If I can find an open interval surrounding a, and in this interval a minus h to a plus h, in this interval a minus h to a plus h, if I find that the function is strictly increasing, if in this interval I find that the function is strictly increasing, then I say that function is increasing at x equal to a, is increasing at x equal to a. A function is said to be increasing at a given point if one can find an open interval surrounding a in which the function is strictly increasing. We say that the function is strictly increasing at x equal to a. Strictly decreasing at a point or decreasing at a point. What it really means is, again, this is a point x equal to a. This is a certain function. And if I can find an open interval surrounding x equal to a, say a minus h to a plus h. If I can find an open interval surrounding x equal to a minus h to a plus h, in which fx is strictly decreasing, I find that fx is strictly decreasing in this interval a minus h to a plus h, then I say fx is decreasing at x equal to a. Then fx is said to be decreasing at x equal to a. Say now, something like this. This is the value of the function at x equal to a. These are kinks. Can you tell me whether this function is increasing at x equal to a? Yes, because I can find an open interval surrounding x equal to a minus h to a plus h, in which the function is strictly increasing. So this function is increasing at x equal to a. Suppose I had a function y equal to fx like this. At x equal to a, this is the value of the function, and again one can find an open interval surrounding x equal to a in which the function is strictly decreasing. So this function is decreasing at x equal to a. Is decreasing at x equal to a, right? Suppose this is the value of the function at x equal to a, say. Can you tell me whether it's increasing or decreasing? Can you find an open interval surrounding x equal to a in which the function is strictly increasing or strictly decreasing? You cannot. In this case, this is the value of the function at x equal to a. It is neither increasing nor decreasing. It's neither increasing nor decreasing at x equal to a. Suppose I had something like this. then at x equal to a, this is the value of the function. Can you find an open interval surrounding x equal to a in which the function is either increasing or strictly decreasing? You cannot. So in this case, again, the function is neither increasing at x equal to a nor decreasing at x equal to a. This is what it means, right? So this is also neither increasing nor decreasing. Nor decreasing at x equal to a, right? Now, if a function is differentiable at a point, say this is x equal to a, the slope of the tangent at x equal to a would be the slope of this line, and f dash stays positive. F dash stays positive. If f dash stays positive, then fx for sure is increasing at x equal to a, increasing at x equal to a. Similarly, this is f dash stay at this point. At this point a, f dash a is the slope of this tangent, and if you find that f dash a is less than 0, if you find that f dash a is less than 0, then the function for sure is decreasing at x equal to a. Is decreasing at x equal to a. Suppose f dash a becomes equal to 0 at x equal to a. What if f dash a becomes 0? Let's examine that. So for sure, if the derivative at a given point is positive, the function is said to be increasing at that point. If the derivative is negative, the function is said to be decreasing at a point. But what if the derivative at a point is equal to 0? Say something like this. The derivative at x equal to a becomes 0. But in the neighborhood of x equal to a, f dash x is positive. Do you find that in the neighborhood of x equal to a, f dash x is positive? At x equal to a, f dash x becomes 0, but in the neighborhood of a, f dash x is positive. To the immediate left of a, f dash x is positive, as you can see. To the immediate right of x equal to a, f dash x is positive. The tangents make acute angles to the left and right of a. Then we find that the function is still increasing at x equal to a. The function is still increasing at x equal to a. Right? Yes or no? Right? If you had, say, something like this. If at a given point, again, f dash x becomes 0 at x equal to a. In this case, f dash a is 0. Slope of the tangent at x equal to a is 0. But to the left of a, f dash x is negative. And to the right of a, f dash x is negative. To the immediate left of a, f dash x is negative. To the right of a, f dash x is negative. F dash x is negative in the neighborhood of x equal to a. Then the function is still said to be decreasing at x equal to a. Function is then said to be decreasing at x equal to a. So if at a given point you find that the derivative is 0, but in the neighborhood of x equal to a, f dashed x is positive, then the function is increasing at a. If at a given a, f dashed x becomes 0, that means f dashed a is 0, but in the neighborhood of x equal to a, on either side of x equal to a, you find that f dashed x is less than 0, the function is said to be decreasing at x equal to a. And in fact, something like this, where at x equal to a, f dashed x becomes 0, but to the left of a and to the right of a, the tangents have opposite signs. To the left of a, f dashed x, and to the right of a, f dashed x have opposite signs, right? In the neighborhood of x equal to a, f dashed x has opposite signs. If f dashed a is becoming 0 and in the neighborhood of a, f dashed x has opposite signs, then the function is said to be neither increasing nor decreasing at x equal to a. Not decreasing at x equal to a, right? So if f dashed a is positive and on either side of x equal to a, f dashed x maintains opposite signs, to the left of a and to the right of a, f dashed x has opposite signs, then we can conclude that the function is neither increasing nor decreasing at x equal to a. This gives us a brief idea of monotonicity, strictly increasing, strictly decreasing. In the next session, we would examine some applications around all of this and get comfortable with these ideas. Thank you so much.